Hey, let's talk about Raviv's practice test for test number 3. So this first one here, we want to find the total resistance. And when we take out the voltage sources to look at the circuit, we have two resistors in series. And what do we do when we have resistors in series? We add them up, and that's how we get 5. This one here, what we can do is actually we can just do KVL. So looking at a big loop, starting over here, we have 4. That's because we're going from negative to positive. So one way we can do it is just looking at the sign that we end up with, and the sign that we end up with going up the loop is the sign that it's going to be. So we're ending here with a positive, so it's going to be a plus 4 plus 2i. And what is I? I is actually equal to this. And remember, I equals V over R. And so we can write 2 times Vx over 4,000. That's what that actually is. And the next element we have is going to be our Vx. And Vx can be found over here because we have it coming from there. And so Vx is going from plus to minus, and so that's going to be a negative Vx. Set that equal to 0, and that gives us Vx is equal to 8 when you plug that in math way or figure it out yourself. And so now we know what our Vx is, and the question is asking us what is I. And so remember that I is equal to V over R, and so we can do 8 over what's our total resistance. We already solved that in the first problem. We have 2 and a 3, and we can just break that up into 2 plus 3. And so 8 over 5 is equal to I. 8 over 5 is 1.6. Alright, so this one here, so this circuit, it's open, right? It's an open circuit, and so the current going in this direction here on this branch is always going to be equal to 0. And if we want to find the voltage, we can use a voltage divisor method. And so we can do VOC is equal to the total times R2 over R1 plus R2. And let's label this one, R1. Let's label this one R2. And so we can do Vs, which is 1.5i times 3 over 2 plus 3 is equal to 0. And oh no, sorry, not equal to 0. We can just write it as that. And then we can simplify it, saying that this is going to be 3i over 5, which is equal to VOC. And what is I? We already said here that I is equal to 0. So VOC is simply going to be equal to 0. This one here is really similar to the problems that we were doing on the first test. So using the same formula that we were doing then, it's going to be y2 minus y1 over x2 minus x1. So same kind of thing. I deleted the professor's notes over here, and I wrote in the times that we're going to. So we have over here 0 to 2, and then 2 to 4, 4 to 8, 8 to 10, 10 to 12, and don't forget to put in those units. And so we'll calculate the current for each one of these. Another thing to remember before we start is that we have a 50 UF here, and the conversion is going to be 1 UF is equal to 1 to the negative 6. So when we have 50 UFs, we can actually write that as 50 times 10 to the negative 5. So that's how we're going to be writing it to calculate the values. Okay, so we want to find the current for this first one, 0 to 2. So IT is equal to, let's do the capacitance all these are going to be the capacitance, so 50 times 10 to the negative fifth times y2 minus y1, so 10 minus 0 over, what's the x? The x is 2 minus 0. And when we do this, this is in milliseconds, so it's actually going to be 2 to the times 10 to the negative third. And when we calculate that, you plug it into Mathway, it's going to be 0.25 amps. And so we can draw that here as 0.25 from 0 to 2. The next one here, just looking at the graph, we can see there's no change. So the current change is going to be 0. You know, you can calculate it if you want. It would be just 10 minus 10 over 4 minus 2, but that would still be equal to 0. So from 4 to 8, I want to write that. And so from 4 to 8, here we have 8 minus 4, times capacitance, so 50 times 10 to the negative fifth times, oh no, I wrote that wrong. Sorry. Okay, so the y is going to be, oh yeah, no, I did do that, right? No, I didn't. Okay, negative 10 minus 10. Negative 10 minus 10 over, and then the x is 8 minus 4 to the negative third, and that is going to give you negative 0.25. And so down here we drew in a 0 from 4 to 2, and then a negative 2.5 from 8 to 4. Continuing on to the next one, you can see no current change in 10 to 8, so IT is equal to 0. So then this last one here, IT is equal to the capacitance times, let's see, 0 minus a negative 10 all over 12 minus 10, which is going to be 2, negative 3, and that once again is going to give us 2.5 like the first one. Capacitance, these are fun. So for your cheat sheet, when these things are in series, like here, we can do 1 over C1 plus 1 over C2 equals 1 over C equivalent, or you can do it like this. This is a little bit easier, I find, in Mathway, just to write it out like that. You add them up and to the negative 1 power, and you're done. Another way that you can look at this when you have the same, if the C's are the same, so like let's say that you have something like this, and these are in series, you know, if these are 4 and this is a 4, you can just add these up, not add them up, but you can look at it and be like, all right, there's 2 of them, and so half of this 4 is going to equal 2, and so that's the total. And so that's what we can actually do right here, looking at these 666. But anyway, so you can do, you know, 1 over 6 plus 1 over 6 plus 1 over 6, and then add that up, and that'll equal 2. Or you can be like, all right, there's 3 of these, they're the same, so a third of a 6 is 2. And so you can kind of just look at it and be like, oh, that equals 2. So redrawing that whole circuit now, this is going to be 4 there. We have, oops, that's a resistor. We have a 2 here, and we have another, what am I doing? We have another 2 here. Those 6s simplified. So now we have a 2 and a 2 that are parallel to each other. So when they're parallel, we just add them up. So our new diagram will look like this. There's a 4 there, and when we add that up to 2 and 2 equals 4. So now this 4 and this 4, these are in series, and we can do the same thing. Half of 4 is 2, and so this total is going to equal 2. I hope I made that clear. Otherwise, if I'm not explaining it correctly, the best way to find, these things in series would be 1 over 4 plus 1 over 4 equals 1 over CEQ. Yep, okay, so that is that. Our final answer is 2. These are awesome, super easy. This is the same thing we were doing for the resistors, maybe last test or the test before it. But anywho, so finding the inductance, so you have a 2 here and a 2 here. So what do? You do 2 parallel 2, which is going to equal 2 times 2, 2 plus 2, which equals 1. So now we have a 1 here. 1 plus 4 is equal to 5. And so our new diagram, you have a 5 here, you have a 5 here, and 5 parallel 5 is equal to 25 over 10, which is going to give you 2.5. Let me just calculate that, make sure I'm not tripping. 25 divided by 10, yeah, 2.5. Perfect. Alright, so this one is the same thing. If you remember, when you have a diagonal like this, you treat it just like it's parallel. So looking at this corner here, we can do 3 plus 9, which is equal to 12. And so then essentially we're looking at it like this, and this is a 12 here, and this is a 12 here, and so 12 parallel 12 is equal to 36. All right, and then we have, oh, I'm sorry, it's not 36. That's 6. Okay, and then so looking at this part here, 3 parallel with 6, let's see, he says it right here is 2. So then our new diagram will be 2, and this is a 6, and then up here we still have a 2 up there, and so 2 parallel with 6 is what? I don't know what that is. 12 divided by 8. 1.5. And then we have this 2 still up here. So 1.5 plus 2 is equal to 3.5. Because, these will be in series now, so we can just add them up. So L equivalent is equal to 3.5. All right, so for here, okay, I'm just gonna write this answer out. The official answer is oops. So that is the official answer, and the explanation. So I is equal to V over R, and the total voltage is 12, And the resistors are 10K, and so 10K is going to be negative third, and this is equal to 1.2. Want to find C. So what we can do is just cross off part of the circuit and only look at that. Don't worry about the 7 for now. And so we can use the same formula that we've been doing, because if you look, this 6 and this C right here, they are actually in series. And so we can keep using that same formula. CEQ is equal to 1 over C1, 1 over C2. And when we plug our values in, that'll give us 1 over 4, which is our CEQ, 1 over 6 plus 1 over C. And solving for that, C is equal to 12, but that's not our final answer because we still have that 7 over there. And so the 7 and the 12, the C and the unknown variable are in parallel, right? And so we know that you add these things up. And so 12 minus 7 is going to give us 5. And that's how we know that this final C is going to equal 5. Because we minus, take away, the 7 that we were going to add into it. All right, so for this one here, oops, that is not correct. Okay, so for here, we want to find the total capacitance. We have an unknown variable C, so using that formula, we can add all of these up. And this is equal to 1 over CT. And what is CT? We are given CT, and so I'm going to erase that. 0.5. And if you plug this into Mathway, you are given C equals 1.